Hi there. My report for my final year was based in the telecommunications sector. I was researching a novel adaptation to the existing OFDM modulation scheme, which I'm sure you're familiar with. In terms of traditional OFDM, you transmit information across every subcarrier in an OFDM block. In index modulation, you activate and deactivate certain subcarriers based on your subcarrier activation ratio, and that means that you can use less of the spectrum. This has advantages where you might be wanting to use less power, or even if you're using the same amount of power, you can reallocate that power. The advantage of OFDM-IM lies in the fact that it utilizes these null carriers and this empty information to transmit more bits in the form of index bits. So whereas traditional OFDM, one block, sends one block of information, in OFDM-IM, it sends the data bits of information along with the corresponding index bits based on that subcarrier activation ratio. One of the primary things that's really great about OFDM-IM is the modular nature of this. So because you can vary the subcarrier activation ratio and you can have theoretically limitless combinations, depending on the channel response of a channel, you can change your subcarrier activation ratio accordingly. This has a lot of applications in a lot of different wireless environments where you might need different subcarrier activation ratios. My project was divided into two parts. The first part was developing an algorithm for OFDM-IM, and a lot of research thereof. Once I had this algorithm and the simulations in MATLAB, I actually ported this to software-defined radios, and that's what's running in the background here. This is run over just a simple line-of-sight channel on a software-defined radio, but it is a proof of concept that it actually works. Through the simulations and through the software-defined radios, which is probably the more important aspect of this, I found that it does hold up with OFDM in terms of bit error rate performance. In terms of frequency offset, it doesn't work as well as OFDM, but it still shows that this could have applications in the telecommunications sector with further research. Research into different subcarrier activation ratios as well is really important. But yeah, thanks.
Orthogonal frequency division multiplexing, as we know it, has been around for the last 15 years. What this project is exploring is a novel adaptation of that technique in the form of OFDM with index modulation, or OFDM-IM for short. OFDM with index modulation essentially splits a typical OFDM block into much smaller sub-blocks, as shown by the diagram here. Each of the sub-blocks has a corresponding subcarrier activation ratio depending on what you choose. Generally, the sizes of the sub-blocks are kept small to avoid computational complexity when developing the codebook, which I'll talk about later. This method of modulation has been around for a while. It was first postulated in about 2008, but recently has been gaining a lot of traction with the advent of 5G as one of the potential modulating techniques. As mentioned before, this project is divided into two parts, the first part being the development of an OFDM-IM algorithm and simulation of this through MATLAB. The second part being the porting of this code to software-defined radios so we can monitor how OFDM-IM functions as a modulation scheme against traditional OFDM. Basically, OFDM-IM can be classified depending on the subcarrier activation ratio, and this is going to be dependent on what size subblock you're using. For example, here, when you're using a subblock of size 4, this shows the corresponding subcarrier indices that are active and the corresponding bit stream that you would send to the encoder. Not only does OFDM-IM send the information on the active subcarriers as shown here, it also interprets at the receiver end the active to inactive subcarriers, and then depending on that will add a corresponding bit stream. This is essentially a way of adding extra data based on what the ratio of active to inactive bits are. A word on the codebook now and how it's created. we need to develop a code book that corresponds the subcarrier activation ratios in the given subblock to additional index streams. So the number of code words is going to be n choose k, and log2 of this number is going to be the amount of additional index bits you can carry. What was used heavily within this project was the 4,8 scheme, and the example here would be that 8 choose 4 gives you 70 possible code words to work with, and the log2 of this value is going to give you 6 additional index bits per subblock. In practice, when we're running through streams of information, we're going to call the first X amount of bits the index bits that we need to then check back to the code book and see what subcarrier activation ratios they compare with. And then in the encoder, what we're going to do is take that ratio and then only put the information on the active subcarriers that we've determined. The decoder is going to perform essentially the inverse operation, whereby it checks the incoming information at the receiver and compares it with our code book, which here is called B, and then determines what it is most likely to be decoded as. Once it has the corresponding subcarrier activation ratio, it can then decode the active data on the active subcarriers and append the index bits at the end of the decoding function. To compare OFDM, IM, and the various schemes that I coded in against the OFDM schemes, I ran them on the same frequency spectrum, and this is what you can see here. On the left, you have the OFDM IM 4,8 scheme, and on the right is just a traditional OFDM scheme. Important to note here is the notion of additional power factor that is applicable in OFDM IM schemes. Because you're not utilizing the entire frequency spectrum and you have these null carriers, you actually have additional power throughput. So the power that you save can be reallocated, as is shown here, or you can simply save it if you're operating under a power saving scheme. What you can see here is that as n and k are equal, which is under traditional OFDM, you get a power factor of 1. And then as k decreases, so there's less active subcarriers in OFDM IM schemes, the power factor is increasing. Once this was all done in MATLAB, the signal was passed through a really simple white noise channel just to ensure that the 8,8 scheme converged with the traditional OFDMA scheme, which would mean that the code was working as intended. A quick note on the modulator and demodulator that we used in the simulations in MATLAB. The simple QAM-mod and QAM-demod functions built into MATLAB were used, as it was beyond the scope of this project to develop a modulator from scratch. In the simulations we ran with BPSK, 4 QAM, 16 QAM, 64 QAM, and 128 QAM. Once we had all of our simulation results in MATLAB and could verify that the OFDM-IM modulator and demodulator were working as intended, it was time to port this to a software-defined radio, which was the second part of the project, and to analyze this in a real-world environment. As mentioned previously, the interface between the software-defined radio and the software itself was LabVIEW. In the specific case of my project, there was already a large library of resources available to Monash University that it had purchased from National Instruments in the form of an OFDM system. And by exploiting the similarities of OFDM and OFDM-IM, I was able to piggyback a lot of the code that was written for these OFDM modules and make them more suitable for OFDM-IM systems. Like I mentioned previously, porting of the code to the software-defined radios involved the manipulation of existing modules, which are shown here. Importing of this code to the software-defined radios to accommodate for index modulation, I only needed to edit the digital modulator in the transmitter block of the OFDM system, which is shown here. What this does is utilize the existing QAM modulator in this OFDM system and strips apart the index bits and reformats it after the modulation. After all the data is properly modulated using our symbol set, which is 64 QAM in this case, and the corresponding null carriers are appropriately deactivated and the information only sent over active subcarriers, this information is ready to be sent to the receiver over the channel. These null carriers are the ones that are highlighted in red in this picture. In the receiver block now, we determine what bit pattern has the most correlation with our codebook, and that's our subcarrier activation ratio. And from that, we can get our index bits. The data is then reorganized so that the data bits are sent into the modulator to be demodulated, and the index bits are saved aside to be appended after the data has been dimmed. And this is now what our output looks like at the receiver end. We now needed to test different channel parameters, one of which was varying the noise of the channel, which is shown here. As you can see, it's much noisier than normal. Another channel parameter that was varied was the frequency offset, which is shown here. And then this was compared with OFDM and OFDM-IM. Here we can see the results of varying the SNR over the channel with respect to bit error performance. As you can see, OFDM and OFDM-IM are quite similar. OFDM performs better at lower levels of SNR, and 4,8 can perform higher at higher levels of SNR. And here you can see the bit error rate versus frequency offset for OFDM-IM and OFDM. As you can see, OFDM-IM actually performs slightly worse than OFDM with the frequency offset. Now, this is because when you are decoding data incorrectly in a given subblock, you don't only lose that one piece of information, you also lose the index bits as well, because the decoder no longer knows what the subcarrier activation ratio is for that subblock. In terms of where this leaves OFDM-IM as a scheme in general now, is that it performs under experimentation about on par with OFDM in a lot of scenarios. So where this could go from here and what benefits it offers is probably adaptivity is pretty important for OFDM-IM. So in scenarios where channel responses may vary, you can adapt the subcarrier activation ratio very easily. Also, it was found that in some cases of using higher order modulation, that the bit error rate performance could be increased, and this was touched on in some other papers too. So a bigger exploration of that, I think, would be more beneficial as well. I think simulating more software-defined radios over a larger network to get a better idea of how this would operate in a more realistic real-world environment would be a great idea as well. And of course, due to the scope of this project, only one subcarrier activation ratio was explored over the software-defined radios. But by exploring more of these, we could also explore the efficiency of the scheme as a whole. So thank you very much for watching this video about orthogonal frequency division multiplexing with index modulation. Hope it was educational. Thanks.